Hello, Tensor friends. Uh, some time ago, quite a while ago actually, I did a video on why is this index on this Christoffel, the symbol, why is it in the upper position? And I got a few nice comments on that, and so I went back and watched it again, and it's really it's not very good. I want to redo it. Okay, so this is an updated version. Me, a lot older, much wiser. No, not really. I'm just older on why that's true. So let's start like this. Let's start with a vector whose components, the scalar components, are contravariant, which you know what that means. They change oppositely of this covariant basis vector. So we're using the summation notation, right? So in 2 dimension, this would be 2 terms. In 3 dimension, would be 4 terms. 3 terms. In space-time, it'd be 4 terms, etc. Ever how many dimensions you got, all right? So let's take a derivative of this vector with respect to a coordinate and arbitrary the coordinate, right? So this is a product, so we have to use the product rule. The first times root of the second plus the second times root of the first, and we get this. So what's unusual about this is that this is the new thing here, right? The derivative of a basis vector with respect to a coordinate, right? And that is actually the definition of the Christoffel, the symbol. Now let's look at this. We've got two free indexes here, I and j, and they're both in the covariant position, the lower position. This looks like it's in the upper position because it's a superscript to the x, but it's not. It's in a denominator, so that makes it covariant. So we have to put our free indexes down, I, j, and we know this is a summation, right? Because the derivative of a vector is a vector. So it's going to have a scalar component and a vector component. So we know it's going to be multiple terms. So we choose some letter here that's not ij. So we pick k. And now since it's going to be a summation, we have to put it in the upper position. So that's the easy answer. It's here because of how we chose our basis, the vectors. Okay, so let's do something here. Let's isolate this Christoffel, the symbol. A way we can do that is to multiply both sides of this by a contravariant basis to vector. Okay, so we did it on both sides. Now this is a scalar, so we can bring that out front, which leaves this. And we know what this is. A basis vector inner product with its reciprocal is the Kronecker delta. All right, so this ties in with the other two videos we've been doing on Kronecker deltas and the contraction of indices. So this just leaves, so the k gets absorbed, right? Gets contracted out, just leaves this in the upper index. So now we have a Christoffel symbol isolated, and it's equal to this. And this is called the Christoffel symbol of the second kind. I don't know why it's the second kind, but that's its name. Okay. Let's do an example of this. Let's do it in polar the coordinates, all right? So here we're going to pick, I'm going to pick one of these I know is non-zero. So m is theta, I is r, j is theta. So now we just follow the indices. So e theta, ei is er, and the coordinate is theta, okay? Now we've done this many times in the videos where we've derived the covariant basis vector and polar, the coordinates, and it's this. But you see here, we have a contravariant. So we say, oh, well, how do we get that? Well, this is one of the easy ways to do it. We know this relationship, right? Basis vector, inner product with its reciprocal is equal to the Kronecker, the delta. So if we write this all out, here's E theta, inner product with its reciprocal, but we don't know what these are, right? These coefficients that go here. Well, what coefficients times this? Now remember, this is orthonormal basis vector. So x hat dot x hat is 1, x hat dot y hat is 0. So we don't have any mixed terms. So what C1 multiplied by this and C2 multiplied by that would give us 1. Well, if you stare at that for a second, you'll see it's pretty obvious. negative sine theta over r and cosine theta over r. Let's try that. All right, so you can see here that this negative takes out that, this r takes out that, we get sine squared theta. This r takes out that, then we get cosine squared theta, and we know this identity is equal to 1. So that worked. So now we have the contravariant, the basis vector e theta. All right, so we go back to our equation. We put that in. We put in what ER, this is ER in polar the coordinates, and we've done this many times also. So we take the derivative, right? So what is the derivative of cosine theta with respect to theta? It's minus the sine theta, so it takes out that negative. And we get sine squared the theta. We're going to pull a r out like this, 1 over r. Derivative of sine is cosine. Cosine times cosine is cosine squared. Once again, we got the identity, 1 over 1, so it's just 1 over r. And that's the right answer. For gamma theta r theta, the answer is 1 over r. That's the right answer, okay? Now, let's go back to this equation here where we had the Christoffel symbol in terms of the contravariant, the basis vector. Well, how can we make this a covariant basis vector? Well, one of the ways you can do that is to use the metric, the tensor, right? So I'm going to multiply both sides by this metric tensor, GMK. See this on both sides? And the metric tensor, you can use it to raise and lower indexes, okay? So this gets contracted out, and this gets contracted out, and so we're left with this. So this becomes a K in this position, this becomes a K in this position. So we have this Christoffel, the symbol, is equal to a covariant basis vector times that same derivative. And this is called the Christoffel symbol of the first kind. So it was first. I don't know. I don't know why they call it that. I think it was. All right, so let's do an example with it. So let's pick the exact same thing. So it would be theta r theta. The I and j was r and theta. Okay. Now we put e theta here. The partial will be r with respect to theta. We know what that is. We just did this. Now you can see immediately you're going to get a much different answer, right? You're going to get r. So by lowering that index to this first position in the covariant position, you don't get the same answer. These two things are not the same. Okay? So I think that's a little bit better than what I did last time. I hope it is. I'll see you later.